So good afternoon, everybody. Also from my side, I'm very delighted to present our current work on Nexus-e in this Pathfinder virtual lunch talk session. So I hope you all already have some snacks and drinks prepared. And in the following 30 minutes, I will aim to answer three main questions. So what is Nexus-e? How can Nexus-e be used? And how does it work exactly? For the first question, I represent the purpose of Nexus-e, its key features and its scope. For the second question, I will briefly outline one case study in which we assessed jointly together with the BFA and two industry partners potential pathways for the future Swiss electricity system and its macroeconomic and environmental impacts. For the last part of this presentation, then, I will present, besides others, the modeling processes in more detail, our efforts to validate Nexus-e and its limitations. So, what is Nexus-e? A bit of background. So I think you're all aware, but in many countries, energy systems are changing fundamentally. So baseload power plants such as coal and nuclear are phased out, and electricity generation becomes increasingly more decentralized and based on renewable sources such as wind and solar power. This leads to open questions in politics, industry, and society. For example, what are appropriate policy measures to accelerate the transition towards a decarbonized electricity system? Which flexible technologies can best balance the fluctuating electricity production of renewable sources, and how to minimize systemic risks in future energy infrastructure? Computer models can be of great help in answering such questions. And at the Energy Science Center of VTH Zurich, we are developing the Nexus-e platform, allowing us to assess scenarios for energy systems transitions. Due to the complexity of the energy system, there have been few attempts to model the interactions between individual components system-wide. And Nexus-e closes this gap and represents energy systems, and in particular its individual components, by combining macroeconomic on the one hand and energy system optimization modeling on the other hand. And the key feature to close this gap is its platform architecture. And this architecture allows components of energy systems to be easily connected to each other in the form of modules via clearly defined interfaces. We therefore see Nexus-e as more of a modeling infrastructure for researchers, students, and industry, which is continuously used and extended. To build such an infrastructure and ensure its accessibility, we have defined three core principles of Nexus-e: modularity, clearly defined interfaces between the individual modules, and transparency. This approach allows us to represent energy systems and the impacts within such complex systems on a much larger scale than conventional isolated modeling approaches. Currently, the platform offers 5 core features that build upon knowledge and methods from different disciplines, such as electrical engineering and macroeconomics, and currently focus mostly on the electricity system. And these 5 core features comprise the electricity system optimization of the centralized and decentralized system, electricity market optimization, grid security assessment, and macroeconomic assessment. I will come back to these core features at a later part of the presentation. Using these core features, Nexus-e is able to present electricity systems in full detail on transmission grid level, including lines, nodes, and generation capacities. Countries are hereby either presented in such full detail or in aggregated form, for example, as a single node that combines national electricity production and demand, or even only as an exogenously fixed electricity flow. In principle, the temporal coverage is unlimited and only depends on input parameters, but currently we typically model the years 2020, 2030, 2040, and 2050. Simulating such multiple years also allows to include path dependency, meaning that the model knows in its 2050 simulation what has happened today, in 2030, but also in 2040. Furthermore, Nexus-e can take different temporal and spatial resolutions depending on the model or module. For example, while the macroeconomy module has an annual and national resolution, the module for investments and operation of centralized energy units has an hourly and nodal resolution. So how can Nexus-e be used? Last year, we completed the pilot and demonstration project, the role of flexibility providers in shaping the future energy system, together with BFE and two industry partners. The goal of the project was to develop a suitable tool with which we can represent the Swiss electricity system holistically. In particular, we wanted to compare centralized and decentralized technologies as options to provide short-term and long-term flexibility. Short-term flexibility balances sub-hourly and hourly deviations in the actual electricity demand and generation, and it supports system stability and frequency control. While on the other hand, long-term flexibility accounts for the daily, weekly, and seasonal needs for generation or oversupply because of outages, weather conditions, or seasonal changes. In particular, we aim to answer 4 research questions. What are potential pathways for the future Swiss electricity system? What is the need for flexibility in such a system and who provides it? And lastly, what are the macroeconomic and environmental impacts of such a system? To address the questions, we defined 3 scenarios. The baseline scenario represents the business as usual and includes expected technical and economic developments, as well as the status quo of the Swiss policies. The nuclear 60 scenarios reflects the uncertainty around the phase-out of nuclear power in Switzerland and assumes that nuclear power plants will be decommissioned after a lifetime of 60 years instead of 50 years in the baseline scenario. The high flexibility scenario simulates the impact of an increased supply of distributed flexibility in the electricity system and assumes lower battery costs and higher potential for demand-side management. In order to visualize our simulation results faster and to make them publicly available, we have developed an interactive visualization tool and made it available on our homepage. And I would like now to use this tool to also present some selected results. So I will now switch to the browser, and please let me know if you don't see the browser. So here you can see this is our homepage, our Nexuse homepage, and we have here the button for the results viewer, and where you can have a look, or where you can have a detailed look at the scenarios which I just described right now. So the baseline, nuclear 60, and the high flexibility scenario. So I will now have a closer look at the total capacity development for the baseline scenario. So what are the potential pathways for the future Swiss electricity system? In the baseline scenario, the loss of nuclear power here in orange is mainly compensated by solar power here in green. We also see that PV batteries are built, but only in 2050, and we actually do not see any additional grid batteries installed. While biomass increases slightly, we do not see any increase in wind capacity. So how does these changes in generation capacity, or what do these changes in generation capacity mean for electricity generation? So for this, we can look at the electricity generation tab, again for the baseline scenario, and from 2015 to 2050 in terawatt hours. And what you can see is that in the baseline scenario, PV cannot compensate for the loss of nuclear power despite its substantial investments. Therefore, at least in our simulation results, Switzerland becomes a heavy net electricity importer in 2040 or 2030, 2040. Then what we can do is we can compare the results for the baseline scenario with another scenario, for example, the nuclear 60. And we can see that the longer lifetime of nuclear power can keep net exports at bay. So due to increased domestic electricity production, especially in 2030 and 2040. Furthermore, we want to understand what is the need for flexibility in that system and which technologies provide the required flexibility. And to do so, we will have a look at seasonal flexibility and daily and hourly flexibility. But first, the seasonal one. To do so, we have a look at the monthly production or electricity generation for 2020. And again, only for the baseline scenario. What you can here see now is the monthly domestic electricity generation in terawatt hours for 2020. And we see very nicely that electricity demand is high in winter, but electricity generation is low, mainly due to the low availability of run-of-river. And this leads to the well-known problem that already today Switzerland is net importer in winter and often or typically a net exporter in summer. Now we can have a look at the same graph for the year 2050. And what we see is that the known problem actually becomes even more drastic. In summer, we can expect a significant overproduction by solar power, while the domestic power deficit will continue to increase in the winter period. In at least, again, in our scenarios and simulation results, the required seasonal flexibility is achieved mainly by imports and exports. So importing in winter and exporting in summer. Then also solar curtailment and operational adjustments of dams to generate more electricity in winter. Besides the seasonal flexibility, we can also have a look at the hourly flexibility for 2020. This always takes a bit of time, but what you can see here is a sunny May week selected, and yes, it's 2020. And what you can see is that there is a lot of electricity export driven by substantial power production by nuclear and run-of-river. Storage dams take advantage of the price peaks in the morning and in the evening. And what is interesting, between May 13 and 15, so during these days, you can see that a lot of electricity got imported, and this is due to low-cost electricity available in a neighboring country. So electricity is imported instead, and pump storage fill up their reservoirs. So how does it change for 2050? We can plot it again, and it's again for the same May week, and you see a much more pronounced diurnal dynamic, as well as between individual days. So during the day, especially during sunny hours, most solar power is exported to neighboring countries, if possible, and pump storage uses excess power to fill reservoirs. And similarly, available battery storage recharges, and flexible loads are shifted to sunny hours. Also, dams provide daily or diurnal flexibility and generate electricity mainly during the night. We can now also have a look at the winter week. I don't know which one it will be. It's probably from 18th September to 24th of December. And you see that the picture looks quite different. So domestic electricity production rarely covers demand, especially during night. So electricity imports are very important during each hour of the week. There are many more results, such as on grid security, or on social and environmental impacts available on the interactive visualization tool, and we will also provide more scenarios in the near future. Coming now back again to the slides. And how does Nexus-e work exactly to create these results? For the presented case study, we use all core features to assess the Swiss electricity system. And in the first step, the electricity system optimization determines investments in new generation and storage technologies based on least cost criteria. In turn, the electricity market optimization uses available existing power plants and new capacities for its dispatch, considering the full range of electricity markets such as the forward market and the intraday market. In turn, the grid security assessment checks the impact of grid lines and transformer failures on the likelihood and severity of blackouts. It also provides suggestions for grid updates if grid security level is lower than today's ones. Finally, the macroeconomic assessment provides insight into how investments in the electricity system change the level of GDP, the output of economic sectors, and CO2 emissions. For the presented case study, we include 14 generation and 3 storage technologies and represent the transmission grid in high detail. So 298 lines, 165 nodes, and 313 generation units in 2020. We also include Germany, France, Italy, and Austria, but in an aggregated form, so as one node only. We include 2 main types of parameters in the input database, so as input parameters, so techno-economic parameters and policies. Techno-economic parameters mainly include the electricity demand and how it will develop until 2050, transmission network details such as lines and nodes, generators, so existing ones today, but also candidate units, then generator and fuel costs, and some weather data. The main policies are like investment subsidies, feed-in tariffs, and CO2 taxes. So we produce outputs for the electricity system, grid security, and social and environmental impacts. I think I've showed them like before in the interactive web viewer. So far, I've mainly focused on the outputs for the electricity system, such as the installed capacity, the electricity generation, and imports and exports, but we can also show the development of prices with an hourly resolution, and also the capacity distribution within Switzerland. So that's for the modeling process. What I've mentioned in the very beginning is that we see Nexus-e as a modeling platform that is continuously used and extended. And also in Pathfinder, Nexus-e will be developed further. And as you maybe have already realized, so far we're mainly focusing on the electricity sector. So the main objective in Pathfinder is to transform Nexus-e from an electricity system to an energy system model. And to do so, we add more sectors of the energy system, including heating, the industrial sector, transportation, and the gas network to the platform. I think we're especially happy to collaborate with new research partners on these tasks who bring in their knowledge and also existing models so that they can connect them to the existing platform architecture. So we don't have to develop models from scratch, but can include existing ones into the platform. Making Nexus-e then an energy system model allows us within the context of Pathfinder to assess the Swiss energy system pathways. And in addition, jointly with other groups, Also within the Pathfinder context, we developed new methodologies for linking models and depict cross-scale interactions with them. So already in an ongoing project, we are linking Nexus-e to EuroCalliope, which is also an energy system optimization model. And this collaboration is extended in Pathfinder. And this link, Calliope, provides the developments of the European energy system, while Nexus-e uses these developments as boundary conditions for a more detailed assessment of the Swiss energy system. New in Pathfinder will be the link to the Expanse model. And here Expanse will use Nexus-e output as boundary conditions for an assessment of municipality level energy systems. So I will not go into more detail what is EuroCalliope and Expanse, because I think they will also have a lunch talk session for themselves. There's also interaction planned with the other models used in Pathfinder, for example, Remap, but it has yet to be defined how this interaction will look like. Besides the main modeling processes and their developments, I want to highlight three more aspects of Nexus-e. And the first one is model validation. And I think this is quite interesting because validation of energy system optimization models is rarely done because they are mostly focusing on time in the future, let's say 2050. So it's difficult for them to validate, but we put a lot of work into the validation of Nexus-e. So what we do is we compare historical data and model output for the year 2015. And on this slide, there are three validation examples. Example 1 presents the monthly electricity production, in light the historical values, and in dark the simulated ones. Example 2 on the top right shows the hydro storage levels, in blue the historical values, and in red the simulated ones. And you can see that due to the perfect forecast in our optimization, dam electricity production shifts more into the winter period with higher electricity prices. Example 3 shows the electricity trading between Switzerland and its neighboring countries. So in general, you can see that the validation shows a quite good agreement between model output and historical values. Of course, it's not exactly the same, but it gives us some more confidence in the results of Nexus-e. Second, the user interfaces. And besides the results web viewer, the user interacts through two main other interfaces with Nexus-e. So the one is that the model code is available on GitLab and accessible on request for all researchers. And we also plan to go fully open source in the second half of 2021. And the other interface is that we have all input and output data collected in one database to ensure a coherent set of inputs across all models in the platform. Third, I also want to highlight the main limitations of Nexus-e. So as you have realized when presenting the case study, so far we neglect sector coupling with the heating and transport sector. We only consider them aggregated as kind of a demand set management potential. And also we have not yet run net zero scenarios for Switzerland and neighboring countries. Fortunately, we addressed both limitations already in ongoing projects and also within Pathfinder. So we are excited to present new scenarios that address both limitations. Another limitation is that we currently focus on Switzerland and represent surrounding countries only in an aggregated form. But addressing these limitations requires only adjusting the input database, as the model code itself is not Swiss specific, so it's more driven by the case study we were assessing. Today, we are also planning to use Nexus-e for other countries. We have open proposals and ongoing discussions with industry partners to pursue this, address this limitation. Lastly, the high spatial and temporal resolution makes Nexus-e very computational heavy, making every scenario run and sensitivity analysis a bit time consuming. And for us, it's feasible to reduce spatial and temporal resolution, for example, in kind of a simplified Nexus-e version. But at the same time, we are also convinced of the benefits of such a detailed analysis, what we're doing right now. Therefore, it's feasible, but not yet planned to offer such a simplified version of Nexus-e. This is already the concluding slide. So on the left side, you can see the full team behind Nexus-e. So thanks to all of them. And then thank you very much for your attention. And I'm open for questions and starting the Q&A session now. Thanks.